Good morning, students. Welcome to Bindu Dhadwal Chemistry Lessons. Our topic for today is chemical properties of aldehydes and ketones. We'll be taking some examples of nucleophilic addition reactions. So let us begin. First reaction is addition of hydrogen cyanide. So aldehydes and ketones react with hydrogen cyanide to form addition products known as cyanohydrin. The oxygen, being more electronegative, will attract the electrons towards itself. As a result, there is a partial positive charge on carbon atom. So negative part of this molecule, Cn negative, will get attracted towards here, whereas the electrons will take up the hydrogen of HCN to form OH and Cn group attached to this double bonded carbonyl group. So the product formed is called cyanohydrin. So let us add HCN to acetaldehyde. The electrons come here. There's a positive charge here. So Cn will come to the carbon and H will go to the oxygen. So we get CH3, C, there's an H attached over here, then this is single bond OH and Cn. So this is cyanohydrin, acetaldehyde, cyanohydrin. Then similarly with acetone, we get CH3, 2CH3 group and OH and Cn. This is cyanohydrin. With benzaldehyde again, C6H5, CH, OH and Cn. This is benzaldehyde cyanohydrin. Reactions occur very slowly with pure HCN. So therefore, it's carried out in presence of base, which acts as catalyst. So base will extract the hydrogen ion of the HCN to generate the nucleophile Cn negative. So when the electrons move here, the Cn gets attached here to form an intermediate with negative charge on oxygen, which will subsequently take the proton to form cyanohydrin, addition of hydrogen cyanide. Cyanohydrins are very useful compounds in organic synthesis. They can be used to prepare many organic compounds. For example, from acetaldehyde cyanohydrin, if we carry out acid hydrolysis, we add water in presence of acid, then this Cn group gets hydrolyzed to COH group and lactic acid is formed. This carbon is alpha, so alpha hydroxy propionic acid is lactic acid. And on subsequent heating in presence of sulfuric acid, this H and this H and this OH gets eliminated as water and we get CH2 double bond C COH. This is acrylic acid or alpha beta unsaturated acid. So we can prepare lactic acid from acetaldehyde with the help of cyanohydrin. We can also prepare acrylic acid. Then if we react this cyanohydrin with ammonia, we get this product CH3, CH, NH2, Cn, and on hydrolysis CH3, CH, NH2, COH. This is alanine. This is an amino group on alpha position. It's an alpha amino acid, alanine. Then again, if we carry out reduction of cyanohydrin and followed by addition of water, we get one amino propane 2O. So we get amino alcohols also. Similarly, the cyanohydrin of benzaldehyde on reduction will produce alpha hydroxy amine, and we can also get mandelic acid by carrying out acid hydrolysis. Addition of sodium bisulfite. So again, we can add sodium bisulfite to this carbonyl group. These electrons move here and the negative part HSO3 comes here and Na goes and gets attached to the oxygen, and later on the Na and H exchange positions to form bisulfite addition products. So if we react acetaldehyde with sodium bisulfite, we will get acetaldehyde sodium bisulfite. If we react ketone with sodium bisulfite, we get acetone sodium bisulfite. So the mechanism is these electrons move here, HSO3 group comes here, Na group goes to oxygen. Then this undergoes proton transfer, proton goes here, Na comes here, so we get sodium sulfite salt along with OH group attached to carbonyl carbon. It may be noted that the position of the equilibrium lies largely to the right for most aldehydes and to the left for most ketones due to steric reasons. Ketones, because of influence of bulky alkyl groups, is less reactive. So reaction equilibrium lies to the left. The bisulfite addition products of aldehydes and ketones are crystalline solids and are water soluble. So as the reaction is reversible, the addition products can be decomposed by mineral acids or aqueous alkalis to give back the original aldehyde or ketone. So this adduct, if we reacted with acid or base, we again get the aldehyde or ketone along with byproducts. So if aldehyde or ketone is present in along with some other products, we can use the addition of sodium bisulfite method for purification of aldehydes and ketones. We add sodium bisulfite, we prepare the adduct, only the aldehyde or ketone will form the adduct. And then we add acid, and this again combines back to give us the original aldehyde and ketone, and the other products are removed in the process. So it's used for purification and separation of aldehydes and ketones from other non-carbonyl compounds. The addition of bisulfite is not undergone by diethyl ketone, acetophenone and benzophenone because of steric hindrance of bulky groups present in these compounds. Reaction with Grignard reagent. So we can also add Grignard reagent to aldehydes and ketones, the carbonyl group. These electrons move here. The negatively charged alkyl group will move to the electrophilic carbon atom, electron deficient carbon atom. The positively charged MgX goes to oxygen. So as a result, OMgX and R is attached to carbon. When we carry out its acid hydrolysis, water breaks up and adds, H comes here, OH comes here. So MgOHX is removed and OH and R group is attached here. So the R group in this compound is from the Grignard reagent. Let's add Grignard reagent to formaldehyde and form the products. Here a negative charge, a positive charge. So this CH3 moves to carbon and MgI moves to oxygen. So we get HCHO MgI and CH3 here. Then on acid hydrolysis, water will break up, H comes here, OH comes here. So we get HCHOH and CH3. Similarly, we can add Grignard reagent to acetone and we get CH3C, CH3, O, MgI and CH3 goes to carbon. So we get CH3 here. Then when we carry out acid hydrolysis, again this bond breaks. H of water comes here, OH comes here. So what we get? CH3, COH, CH3 and CH3. This is a tertiary alcohol. So if we add Grignard reagent to formaldehyde, we get a primary alcohol. If we add Grignard reagent to acetaldehyde, we will get secondary alcohol. And if we add Grignard reagent to ketones, we get tertiary alcohols. So Grignard reagent can be used to prepare all kind of alcohols. Addition of alcohols. So aldehydes react with alcohols in the presence of dry hydrogen chloride gas to give geminal dialkoxy compounds. These compounds are called acetal. So the electrons move here, negative charge to oxygen, hydrogen will move to negatively charged oxygen, and OR group moves to electron deficient carbon. So we get hemiacetal. Again, in presence of another alcohol, in presence of dry HCl gas, the H of alcohol and OH of hemiacetal will combine to form water. Water is eliminated and we get our CH2OR groups. This is dialkoxy compound. Geminal, on the same carbon, two alkoxy groups are attached. So it's a geminal dialkoxy compound. It is known as acetal. Aldehyde will give acetal, ketone will give ketal. So let's do this reaction. Acetaldehyde plus ethyl alcohol, electron move here, negative charge, H goes here, and OC2H5 comes to electron deficient carbon atom. So we get CH3CH, OC2H5 and OH. Again, on reaction with C2H5OH, the OH and H combine to form water, and C2H5, OC2H5 group gets attached here. So we get CH3CH, 2OC2H5, OC2H5, diethoxy acetal. Now, the dry hydrogen chloride serves two purposes. Number one, it protonates the oxygen of the carbonyl group and therefore increases the electrophilicity, positive charge on the carbonyl carbon, facilitating the addition of nucleophile, attack of alcohol molecule. Also, the dry hydrogen chloride will absorb the water formed in the reaction and therefore drive the equilibrium to the forward. This is a reversible reaction. If one of the product is removed, reaction will move to the forward direction. So dry hydrogen chloride serves these two purposes. The above reactions are reversible and therefore the acetals formed can be decomposed by dilute mineral acids to give back the original aldehydes. If instead of two molecules of monohydric alcohols, a dihydric alcohol is used, then cyclic acetals are formed. These water will combine and a cyclic product will be formed. This is cyclic acetal. Similarly, this is cyclic ketal from ethylene glycol. The above reactions are reversible. Acetals and ketals are hydrolyzed with aqueous mineral acids to regenerate the aldehydes and ketones. Second category is nucleophilic addition reactions followed by loss of water. We will add a molecule and then in the next step water will be eliminated. Under this category, let us do one reaction, addition of ammonia derivative. So ammonia has 3 hydrogens. If we replace one hydrogen with a group, let's say Z, then this compound is ammonia derivative NH2Z. So the reaction goes on like this. In the carbonyl group, the electrons move to the electronegative oxygen atom, thereby creating a negative charge on the oxygen and positive charge on the carbon. The H of the NH2Z will get attached to oxygen and the NHZ gets attached to electron deficient carbon. So we get this tetrahedral addition product, OH and NHZ. But this in the presence of H plus ions, this OH will combine with the H of NHZ to form water. So water is eliminated and this double bond NZ is formed. Now this reaction is otherwise reversible, but removal of water occurs so fast that the reaction ultimately shifts towards the forward reaction. Also write this reaction simply as a one-step reaction where the double bonded oxygen reacts with the two hydrogens of NH2 group to form water in the presence of acid, and these two combine with a double bond NZ. Carbon double bond NZ is formed with the elimination of water. Hydroxylamine. So the ammonia derivative is hydroxylamine, in which the group Z is OH. So when we react it with an aldehyde, so the H2 of the hydroxylamine will react with the O of the aldehyde to form water, and RCH double bond NOH is formed. NOH group is the oxime group, so the resulting compound is oxime. Similarly, if we replace the H of ammonia with NH2 group, we get NH2, which is called hydrazine. So when we react it with aldehyde, the oxygen of RCHO and the H2 of NH2 will combine to form water, and we get RCH double bond NH2. This is hydrazone. Similarly, if the H of hydrazine is replaced with a phenyl group, this is phenyl hydrazine. Phenyl hydrazine. And if we react aldehyde with phenyl hydrazine, we get phenyl hydrazone. RCH double bond NHC6H5. We replace the H of hydrazine with 2,4-dinitrophenyl group, and we get 2,4-dinitrophenyl hydrazine, and with aldehyde it will form 2,4-dinitrophenyl hydrazone. Similarly, with semicarbazide, again the H2 of NH2 group will react with O of the RCHO group to form RCH double bond NHCONH2. This group, when we replace H with CONH2 group of hydrazine, we get semicarbazide, and the product will be semicarbazone of aldehyde. So for these reactions, we say that reaction occurs in a mildly acidic medium. The optimum pH of the medium should be between 3 and 4. Let's take a few examples where we react an aldehyde with the ammonia derivative. So first ammonia derivative we take up is hydroxylamine. So reaction of aldehyde with hydroxylamine. So the O of aldehyde and H2 of hydroxylamine will combine to form water, and CH3CH double bond NOH. Acetaldoxime. Acetald word is from acetaldehyde. Oxime word is from NOH group is formed. Similarly, if we react cyclohexanone with hydroxylamine, so O and H2 will combine to form water, and double bond NOH is formed. This is cyclohexanone oxime. Reaction with hydrazine. So O and H2 will form water, and CH3 double bond NH2. This is acetone hydrazone along with water. Reaction with phenyl hydrazine, again O with the H2 of phenyl hydrazine to form water, and C double bond N NHC6H5. This is acetaldehyde phenyl hydrazone. Reaction with 2,4-dinitrophenyl hydrazine. So this is hydrazine. This is 2,4-dinitrophenyl group attached to it. So the O of acetaldehyde and H2 of 2,4-dinitrophenyl hydrazine will combine to form water, and we get CH3CH double bond N single bond NH C6H4 NO2 NO2. This acts in the presence. This happens in the presence of acid. Water is taken out, and we get 2,4-dinitrophenyl hydrazone of acetaldehyde. Acetaldehyde 2,4-dinitrophenyl hydrazone. These products are yellow, orange, or red colored crystalline compounds. These are also called DNP derivatives and can be used for identification of aldehydes and ketones. If there's a compound which is an aldehyde or ketone, it will give this coloration, and so it can be identified. Other compounds will not give this color. Reaction with semicarbazide, NH2NH of hydrazine, and one H is replaced by CONH2 group. We get semicarbazide. When this reacts with aldehyde, we get semicarbazone. So O and H2 will combine to form water, and C double bond N single bond NHCONH2. This compound is acetaldehyde semicarbazone. Reaction with ammonia. So aldehydes except formaldehyde react with ammonia to form aldehyde ammonia adducts. So these electrons move here, negative charge on oxygen, positive charge on carbon. So H of ammonia will go to O, and remaining NH2 goes to C. So we get CH3CHOH NH2. Now this is the adduct, but on warming with water, the OH will react with the H to form water. So what we get is a double bond here, CH3CH double bond NH. This is acetaldehyde. Formaldehyde reacts with ammonia to form hexamethylene tetraamine, which is also called urotropine. And uro comes from urine, so it is used as a medicine to treat urinary infections. So formaldehyde, 6 molecules, react with 4 molecules of ammonia to form urotropine, hexamethylene tetraamine, along with 6 water molecules. This urotropine is unique in its structure. 4 nitrogens will be attached through methylene groups. So 1 nitrogen will be bonded to 3 methylene groups, each methylene group to another nitrogen. This nitrogen through methylene will be attached to another nitrogen. So in all 4 nitrogens and 6 methylene groups. This product is urotropine. We can also carry out nitration of urotropine to form under controlled condition to form a very well-known explosive compound, which is RDX. You must have heard in some explosions RDX is being used. This RDX is, the full form is Research and Development Explosives, and this is formed from urotropine by its nitration. So urotropine on nitration will form tricyclo, it's a cyclic compound, cyclotrimethylene trinitroamine. It is also called cyclonite or simply RDX. Acetone reacts with amine, electrons move here, H goes here, NH2 comes here, but this further combines with another acetone. Alpha hydrogen of this acetone will react with OH to form water, and this gets attached here. We get CH3, CH3, CH2, CO, CH3 and NH2. This is 1, 2, 3, 4 amino, 4 methyl pentane 2-one. This is also called diacetonamine. Benzaldehyde will react with ammonia, C6H5CHN, similarly C6H5CH double bond N, and this is CH and C6H5. This is called hydrobenzaldehyde. Is formed. Hydrobenzaldehyde along with 3 water molecules. Reaction with primary amines. Again, O of aldehyde and H2 of primary amines will combine to form water, and we get a product which is called Schiff's base. Similarly, benzaldehyde will react with aniline, water will be eliminated, and we get benzaniline, C6H5CH double bond and C6H5 plus water. So that's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.